In the previous section, we have discussed about some of the bridging loops and the alternatives to stop those bridging loops, and in that we are going to use STP. Now probably in this section we'll discuss about what is STP, some basic introduction to that STP and how it is going to prevent the loops, and what are the step-by-step process it is going to going with when it comes to selecting the forwarding or the blocking ports. So the first thing, STP stands for Spanning Tree Protocol, and Spanning Tree Protocol, as per IEEE, it's 802.1d standard, which was initially developed by Digital Equipment Corporation, but later on it has been made as a standard. So it's a standard protocol which runs on every switch by default. It runs where it is going to find the redundant links. Let's say if you have 4 links, it's going to put any one of the link into forwarding, and automatically all the remaining links will be put into blocking state. So which means they don't forward any traffic. Now STP is going to help us in preventing those issues like broadcast storms, multiple frame copies, and data instability. That's a max table instability. So it's going to prevent the loops which generally happens if you have multiple links between the switches by putting some ports into blocking state. And STP is enabled by default in all the Cisco Catalyst switches. So now in this here we are going to see how exactly the STP is going to work. So how the STP is going to work, the entire STP process happens in 3 different steps. So the first step is selecting the root bridge, selecting the root port, and then selecting the ports, designated ports, that's what we call as forwarding ports, and then selecting the blocking ports, the non-designated ports. So there are few things we need to understand before we actually get into the complete spanning tree process. So let us start one by one. So the first step, selecting the root bridge. Now to understand this process, I'm going to take some default selection of 3 switches. You can take more than that. Now I got a switch 1, switch 2, and switch 3, and I want to understand how STP is going to work in this scenario. So in fact, whatever the topology, it's going to work in the same fashion. So let's take an example. I got a user connecting on switch 1, switch 2, and there is a user on switch 3. It's going to generate a broadcast request, and the broadcast goes to switch 1 send back to switch 3, and switch 3 will send back to switch 2, and then it will repeat. So which means in this scenario there is a possibility of loops. Now I want to understand how STP is going to prevent in this scenario, or it can be any scenario, it's going to work same, but I'm going to take this as my sample topology, which is which I'm using here. Now the first step, let's take an example. I got 3 different switches. Now the first step here will be selecting the root bridge. That's the root bridge. Root bridge is like a central switch where it is like a reference point from where every other switch can decide what ports it has to put into forwarding state. It's just like, when it comes to calculation of deciding the forwarding ports or the blocking ports, they need to make any one switch as a centralized switch, or a root, we call it as here. Now what they do is they do some elections. Now switch 1, switch 2, switch 3, what they do is they say that they undergo some election process where they decide that any switch, whichever the switch is having the best bridge ID, will be considered as the root bridge. So which means whichever the switch is having the best information or the best bridge ID will become the root bridge. Now they keep on sending some hello messages between them. Now we call them as BPDU messages. Now every switch will exchange their own bridge ID information by using some bridge protocol data unit messages, which are sent for every 2 seconds. Now every switch will advertise itself as a root bridge. So let's take an example. The priority value. So the bridge ID is actually a priority value and the MAC address. So assume that now whichever the switch is having the least value will be considered as a best value here. Now in my scenario, let's take an example. The switch 1 is having the priority value of 32768. Let's take an example. And the priority value of the switch 2 is 4096. And assume the priority value of the switch 3 is 8192. Out of these 3 switches, any one has to become the root. So whichever the switch is having the least priority value, that will be considered as the best. Now in my scenario, it is 4,000, 32,000, 8,000. So which is the least? So 4,000 is the least. So switch 2 will say that I'm having a better bridge ID than other two switches in the network. So I'm going to become the root bridge. So everyone will agree on that. Everyone say that, okay, who is a root bridge? Switch 2 is a root bridge. Switch 2 is the root bridge, and switch 2 is the root bridge. So everyone come to a conclusion initially. So what if all the switches have the same priority value? And the default priority value on the Cisco switches is 32768. So that we can verify later on. In the next video, we'll be getting into that more in detail, the verification process. Now, what if all the devices have the same priority value? So let's take an example. The switch 1 is having the priority value of 32768, switch 2 and switch 3 all having the same priority value. In that case, the tiebreaker will be the MAC address of the switch. Now, every switch will have its own MAC address, and we can verify with a command called show version. There is something called base Ethernet MAC address. We'll verify this when we get back to the labs again. So whichever the switch is having the least MAC, that will be considered as the root bridge. Now in my scenario, if I assume the MAC address of this device is 0001, in fact it's a 12-digit number, I'm not writing that complete numbers. If I assume the MAC address of this device is 0002 and the MAC address of this device is 0003, in that case, whichever the switch is having the least MAC, that will be considered as a root bridge. Now in my scenario, you have to compare the first number. If the first number is same, check the second number is same, check the third number. That's how you have to verify. Now in this scenario, as the priority value is same, the tiebreaker is a MAC address. Now in this scenario, the switch 1 will be elected as a root bridge. So the first step all the switches will do whenever you power on the switch is they keep on sending their BPDU messages, and in that BPDU messages they will advertise their own bridge ID information, saying that this is my bridge ID information, and what is your bridge ID information. So they will compare their own bridge ID and the remote bridge ID, and they will come to a conclusion that who is a root bridge? Switch 1 is a root bridge. Switch 1 is a root bridge. So they all come to a conclusion of a common root bridge in your network. So there will be only one root bridge. That's something you need to know. So you can have only one root bridge. That's it. Even if you have 20 switches, let's say if there are some 20 switches in the LAN, there will be only one root bridge, and all the remaining will be considered as non-root bridges. Now all the remaining switches will be considered as a non-root bridges. Okay, so let me just draw the same diagram here just to go with the step-by-step process. Now in my scenario, I'm going to take some 3 devices, switch 1 and then switch 2 and then switch 3, and I'm assuming the MAC address of this device is 0001 and this is 0003 and then 0002, and also assuming that the priority value is same, which is default. So we can also change the priority value. So that's something I'll discuss later on. So we can even change the priority value, just go with the default as of now, and then we have some connection between the switches. And I'm assuming it's port number 20 and port number 21 and port number 22, same ports on both the sides, or it can be different port numbers as well. Now in my scenario, based on this is a root bridge. That's what we decided to go with. Now every LAN will have only one root bridge. As I said, if you have some 20 devices, let's say there are some 20 switches in my LAN, assume that there will be only one root bridge, and all the remaining 19 will be considered as a non-root bridges. Okay. So the next step, selecting the root port. Now this is really important to understand here, selecting the root port, because now every non-root bridge looks the best way to go to the root bridge. Now in my scenario, if I assume this is a root bridge because this is having the best bridge ID, now all the remaining switches will be considered as a non-root bridges. Now every non-root bridge looks the best way to go to the root bridge. So they have to look the best way. So this is one route they can go, and there is another route they can go like this. Out of these two routes, any one can be the best. If I assume that this is the best, there are some conditions for that. I will come back to the conditions. So there are two ports which will take you to the root bridge. Now they will decide out of these two ports whichever is the best. If I assume this is the best, in that case this port will be considered as a root port. So root port is the shortest path to the root bridge, which will take you to the root bridge, and the best path to the root bridge, we can say. So every non-root bridge looks the best way to go to the root bridge. That's what they will do, or we can say the shortest path to the root bridge is considered as a root port. But now the question is, based on what conditions it is going to decide or select the root port. So there are three different conditions we have here. The first thing, they are going to see the cost, the bandwidth. Now there are some default cost values here. If you are using 10 Mbps link, the default port cost will be 100. If you're using 100 Mbps, the cost will be 19. If you're using 1 gig link, the default cost will be 4. If you're using 4 gig link, the default cost will be considered as 2. So depending upon the type of the link we are using. Now in this scenario, I'm assuming that I'm using 100 Mbps links, which is something default we use most of the time. So I'm assuming all the links are 100 Mbps links. Now if I'm using some 100 Mbps links, now who is the root bridge? This is my root. Every non-root bridge looks the best way to go to the root bridge, and the cost to reach on each and every port is 19. Based on 100 Mbps, the cost is 19. So if I go from this way, let's say I'm going from this route, what's the total cost? It's going to be 19. And if I go from the other route, let's say I'm going to from this route. If I go from this route, the green one, the total cost is going to cost me 38, because 19 plus 19, how much it is? 38. So there are two possible routes to reach the root bridge. Out of these two possible routes, the one is 19 and the other one is 38. So whichever the route is having the least, again, remember again, least is always preferred in the spanning tree. The least cost will be considered as a best route. So in other words, we can say higher bandwidth will be more preferred. But here when it comes to calculation, we always prefer least cost here. So shortest path or the least cost. So in this scenario, this port will be considered as a root port, because to reach from every non-root bridge looks the best way to go to the root bridge, and this is the shortest path to the root bridge in terms of cost. Now the same way, now this is a root port on switch 2, and similar way the same thing will be done by switch 3 also. Switch 3, it will see if it goes from here, the cost is 19. If it goes from here, it will be 19 plus 19, it's going to be 38. So it will say that this is the shortest path, so it will write down this port as a root port. So every non-root bridge will have one root port. So which means if I take an example of I'm having one root bridge and I got 19 non-root bridges, in that case there will be 19 root ports, because every non-root bridge will have one mandatory root port, and that will be only one, not more than one. So the first condition, it is going to see the shortest path. For the shortest path to the root bridge, it's going to see the cost. Now there might be cases where there is a tie in the cost. What if there is a tie in the cost? So in this scenario, this is a root port, that's what we decided, root port. And then in this scenario, the switch to this is a root port because of the shortest path. But what if there's a tie in the cost? So when there is a tie in the cost, let's take an example. I got a root bridge here and it is connecting to some two different switches, and then it's connecting back again to another switch. Now in this scenario, I got two different switches, a root bridge. Now if I go with all Ethernet ports, the default cost, and the default cost from both the sides will be 19 plus 19, 38. So if I go from this way, what's the overall cost? 38. And if I go from the alternate route, the overall cost is how much? 38. Now when there is a tie in the cost, in that case, now both the ports will not be a root port again. Again, don't think that both will be a root port. There will be only one root port. So now the next condition, they are going to see the forwarding. The first condition is cost, and then if there is a tie in the cost, it's going to see the forwarding bridge ID, forwarding switch bridge ID. Okay, so if assume that the priority value of this switch is 4096 and the priority value of this switch is 8192, it's going to see the bridge ID. Bridge ID means first it will see the priority value, and if there is a tie in the priority value, then it will see the MAC address. So which means this is having a better priority value. In that case, this will be the root port. Okay, so this port, so it's going to see the forwarding switch bridge ID. Forwarding means upstream bridge ID, not the local, upstream bridge ID. Now, in case if there is a tie in the priority value, if I assume the priority value of these two devices are 32768 and 32768, because by default, when you talk about bridge ID, mostly if you go with the default values, the priority value will be same. Then the tiebreaker will be the MAC address. So bridge ID means first it will see the priority value. If there's a tie in the priority value, then it is going to see the MAC address. So forwarding switch bridge ID. If I assume the MAC address of these two devices is 2C and 2D, and assuming that the priority value is same, then the tiebreaker will be the MAC address. So the MAC address of 2C is less than 2D, so the least will win, and this port will be considered as a root port. So that will be the next condition it is going to see. So the forwarding device MAC address. So this is my root port. So based on priority value or MAC address. So if there's a tie in the priority value, the tiebreaker will be the MAC address. So what if there is a tie in the MAC or priority value, there is a tie, then the MAC, and what if there is a tie in the MAC? So is there any possibility for tie in the MAC? Let's take one more example here. Let's say I got a diagram of root, and then I got a switch connecting to this one, and the MAC address is same, and also priority value. Now in this scenario, if I just go with the default cost values, the cost is 19, 19, 19. So if I go from this route, the cost is 38, and if I go from this way on the same port, the cost is 38. So the first condition, that tie in the cost, then the second condition, it is going to see the priority value in the MAC address. So here it is actually coming on the same switch, so probably there is a tie in the forwarding bridge ID also. In that case, it is going to see the third condition will be forwarding port number. That's what upstream port number we can say. Now out of these two conditions, it is going to see what is the port number you are connecting here. Let's say I'm connecting on port number 23 and I'm connecting port number 24. So it's going to see the upstream port number, and based on that, the least port number will be more preferred. Now in this scenario, this port will be considered as a root port. So even though maybe you are connecting port number 20 here, maybe port number 10 here. So it's not going to see the local ports, it's going to see the upstream ports, okay, not the local ports. So out of these two ports, the 23 is the least one, upstream port, so this port will be considered as a root port. So this is the third condition it is going to see when it decides the root port. Now these are the three main conditions we need to know. First, it is going to see the cost. If there's a tie in the cost, it's going to see the forwarding bridge ID. In that, it will see the priority value. If there is a tie in the priority value, the second condition, it will see the MAC. And then if there's a tie in the MAC and priority value, if they are coming from the same switch, it is going to see the port number, and that too the forwarding or the upstream switch port number.